Alright, so today we're going over derivatives versus graphs. So this section is essentially understanding how to look at a derivative graph or a function graph and knowing what to look for, especially when a question asks you something. So some few things to go over. So let's say we have a f of x graph, function graph of this would be x squared minus like 3. And that means that the derivative graph would be a linear function because essentially this would be like a velocity. The derivative graph would be decreasing because it decreases in this interval right here on the left, and then it starts increasing. So which is shows in the velocity graph in which is positive here and negative here. And then the second derivative would show basically an acceleration, the derivative of the first derivative graph. So we could kind of see the slope of the first derivative graph is kind of constant everywhere. That's why the second derivative graph is actually just one horizontal line, which could be like y equals 2 or y equals 1. Which essentially is the slope of the first derivative. The first derivative is the slope of f of x. And now let's go over first these few rules. So let's say f prime of x is more than 0. That means that function f of x is increasing. And if f prime of x is less than 0, that means function f of x is decreasing. And let's go over here. F double prime of x is more than 0. That means the function is concave up. Now concave up means that the function is accelerating, and concave up looks something like this. Just think of like a U. If it's curving towards the top, then it's concave up. And if f double prime is less than 0, then it's concave down. Concave down is just think of just an upside down U or an N. It's pointing down or concaving down. And we should also talk about inflection points. Inflection points is essentially when the concavity of a graph changes. So it could be also when f double prime reaches has a 0, or when f prime reaches a maximum or minimum point, or of course when f of x reaches a concavity change, which could be depicted by this graph on the bottom left. So this at x equals 0, we could see that the concavity is changing. It's going from concaving down to concaving up. Now that shows in inflection points because the concavity is changing right there. In which at that point f double prime of the function would be 0, no matter what the velocity is. Alright, so let's take a look at number 1 and 2. So number 1, 2 is use the given graphs of f to find the following, and then we have f is increasing, decreasing, and then we have to depict where it's concaving up, concaving down, and then the points of inflection. So let's first start with the first graph. So let's mark it down right here, A. Let me actually change my brush size. So let's find for graph A where f is increasing. So both these graphs are f of x. So f is increasing, we could see on the interval from 1 to 3. And it's also increasing from the interval of 4 to 6. So we could write 1 to 3 and 4 to 6. And for B, we have to find out on which intervals is f is decreasing, which would just be the opposite. It would be 0 to 1 as our first interval. And then we would have it's also decreasing on interval 3 to 4. And then it's also, oh, that's it. It's only decreasing on 2 intervals. So let's go to C. And C is on the open intervals on which f is concave up. So as we talked about, concave up on a graph would essentially just mean it's kind of facing up, or the graph is facing up-ish. So we can see it's concave up right here, and it's not concave up right here. As you could see, it is like a sharp corner here. A good thing to know is when a sharp corner does appear, it's either both limits from both sides are concave in the same direction, which means that the function is not differentiable. But so we depicted that it's concave up on this interval, which is 0 to about, I'd say 2. So if it's concave up from 0 to 2 interval. And that is the only interval is concave up. Let's go to D. D is open interval concave down. So we see it's concave down over here, and it's concave down at the end over here. So over here is from x value of 2 to the x value of 4. So it's concave down from 2 to 4, and it's concave down again from 4 to 6. So you could also say it's concave down from 2 to 6, but the 2 to 4 and 4 to 6 kind of separates the fact that it shows that there is a part of the function here that's not differentiable. But now let's go to E. So E is the coordinates of the points of inflection. So as we talked about, the points of inflection is essentially when the concavity changes. So we can see there's only one point in this graph in which the concavity changes. It's between this little area over here. So when the concavity changes, the graph looks something like this over there. It goes from concave up to concave down. So that means the concavity would have to change somewhere around here, because that's when the function starts going the opposite way. So if we look at the actual graph, it would just be like right here, which is x equals 2. So our points of inflection would be x equals 2. Or you could just write 2. And now let's move on to graph 2. So graph 2, let's look at A, which is on which open intervals is f increasing. So we can see it's increasing from 0 to 1. It's increasing from 3 to 5. And it's still increasing actually from 5 to 7. So we could write 0 to 1 and then 3 to 5 and also 5 to 7. And the reason why we don't make this 3 to 7 is because this function here, it reaches, if you think of like an x cubed function, it goes kind of like that. You can't eyeball like see it, but it does flatline at a like very momentarily, in which when it flatlines, it's not actually increasing. So we do, because you could also see that the velocity goes from, or the slope goes from such a fast slope to such a slow slope, which means that has to go through negative. So basically, that's why we have that separated. And now we go to B on the open intervals in which f is decreasing. So f is decreasing on the opposite intervals, which is going to be 1 to 3. And I believe that's the only one, right? Yeah, 1 to 3 is the only intervals at decreasing. C is going to be concave upward. So concave up, as we talked about, is going to be when it faces up. And that's going to be around from x equals 2 to around x equals 4. So we're going to say 2 to 4. And then that's concave down there. It's concave up again here. So we can say it's concave up from point over here, just 1, 2, 3, 4, 5, 5 to 7. And I believe that's the only place, yeah, it's the only place concave up. Now let's go to D, which is concave down. So we know it's concave down from over here, from interval 0 to 2. And it's also concave down momentarily over here, which is going to be from the interval of 2, 3, 4, 4 to 5. And now E is going to be all the way down here, which is the points of inflection, which is just essentially when the concavity changes. So we know concavity changes over here, which is x equals 2, or x equals 2, and it also changes over here. It goes from concave up to concave down. So this is going to be x equals 4, and it changes one more time. It changes from concave down to concave up, which is going to be over here, which is x equals 5. And that would be our points of inflection for number 2. So let's take a look at number 9, 10, 11, 12, 13, 14. We might not get to a lot of these questions, but So basically, here we have to find the intervals in which f is decreasing and increasing, and then match them up with the local maximum or minimum. And so basically, to get to finding where it's increasing or decreasing, we have to find f prime, which is the derivative, and we can figure out the parts in the graph where has a horizontal tangent, which would give us the local maxima and minimums, and then finding out where it decreases and whatnot. So we'll find the derivative first. So if we find derivative using the power rule of number 9, we're going to have actually 6x squared minus 30x plus 24. And we could also now find the zeros of this, which would tell us where f prime is equal to 0. So we could first factor out 6 because we don't necessarily need that. We have x squared minus 5x plus 4. And then if we factor that out, which we're going to need is going to be x minus 4 and minus 1. So x equals 1 and 4 are our critical points here. So now we need to find out if it's where it's decreasing and increasing. So we have, let's say, let's draw a little graph to visualize it. So we have x equals 1 over here, and then we have 4 right here. So at 1 and 4, we need to figure out if it's decreasing on this left side, and what's happening in the between, and then what's happening to the right. So in order to find that out, we could just plug in any number here into a derivative and then see if it's negative or positive. So let's plug in to the left of 1, let's plug in 0 into x squared plus minus 5x plus 4. So that would give us 0 minus 0 plus 4, which is a positive answer, which means that it is increasing to the left of, the slope is positive to the left of 1, which means that it could be something like that. We could just write it down. And so first we know that in the interval of negative infinity to 1, it's increasing. And what we should also do is find the points actually for this. So what we could do is take x equals 1 and 4 and plug it into our original equation so we could just get the point. So we plug 1 into the original equation, we would get 2, 1 to the third power, which is 2, minus 15, x squared, which is just 15, plus 24, minus 5. And if we simplify that, we're going to have 26 minus 20, which is going to be 6. So our first point is going to be 1, comma 6. And then if we plug in 4 to original equation, we're going to have 4 cubed, which is going to be 64, times 2, minus 15 times 16, plus 24 times 4, which is going to be approximately 98, and then minus 5. Now, we might have to use a calculator for this, actually. So 64 times 2 is going to be 128, minus 15 times 16, which is going to be 240, plus 96, minus 5. So we're going to have now 128 plus 96 is going to be 224, minus 240, and minus 5. So we're going to end up with negative 21, and this is going to be 4 comma negative 21 here. So now we have our 2 points. Why don't we actually plot them? So we have 1 comma 6 over here, and let's do 4 comma negative 21 down here. So we kind of have those reference points here so we could tell. So we could also redirect this graph up here. So now we know it's increasing in that little interval. And let's find in which it's decreasing, even though we could also estimate in which interval is decreasing. Because since it's a cube function, it would go down here and then up. But let's do the math anyways. So let's plug in a number from the interval of 1 to 4 and to a derivative, and then figure out if it's positive or negative. So let's plug in 2 into the derivative equation. So it's going to be 2 squared. 2 squared minus 5 times 2 plus 4. So we're going to have 4 minus 10 plus 4. We're going to have negative 2, and that's a negative number, which means that in the interval of 1 to 4, it's decreasing. So we could draw that. And now we could plug in a number higher than 4 to show that it's increasing on the interval from 4 to infinity, but you could also make the general assumption that it is also true that past 4 from to 4 to infinity it's increasing. So both of these intervals increasing, and then in the interval of 1 to 4 the function is decreasing. Alright, so let's do a different question here. So we did number 9. We're going to skip number 10 and 11 because they're kind of the same. We're going to try number 12 because it involves the product rule and fractional exponent. So we have x to 2/3 power times x minus 3. So let's write out the product rule. That's going to be f prime g plus fg prime. And now we need to find out the derivative. And then solve for x, so we could find out the horizontal tangents, which will be the minimum and maximums, and then we could find out the rest. So let's find out derivative first. It's going to be f prime, which is going to be, and also this is f and this is g, be 2/3 x to negative 1/3 power, and that's going to be multiplied by g, which is going to be x minus 3, plus f, which is going to be x to 2/3 power multiplied by g prime, which is just going to be 1. And now let's simplify. So let's actually rewrite 2/3 and x to negative 1/3 power. That's going to be 2 to the 3 cube root of x. So now let's simplify. So if we multiply it out, we're going to have 2x over 3 to the cube root of x minus 3, or rather 2 over cube root of x plus x to 2/3 power. And this would be our derivative function, and we could solve even further for x so that we could make it a lot easier for us. So what we should do is let's move this little thing over here to the right side. So we're going to have 2x to the 3 cube root of x plus x to 2 over 3 power, and then equals 2 over cube root of x. So we could simplify this over here. So 2x over 3. So we could take out the 2 over 3. So we have 2 over 3. It's x over 1 over 3. That would be 1 minus 1 over 3, which would give us an exponent of 2/3 x 2 over 3, and then plus x 2 over 3. If we combine them, we're going to have 5 over 3 x to 2/3 power. And that's going to be equal to 2 over cube root of x. And now what we could do is multiply the cube root of x to the other side. The cube root of x is just x to 1/3 power. So we multiply to the other side, we're going to have 5 over 3, x is equal to 2. Now let's multiply the 3 to the other side. So we're going to have 5x is equal to 6. And we divide by 5 on both sides. We're going to have x is equal to 6 over 5. And so x is equal to 6 over 5 is our only horizontal tangent on this graph. So what we could do now is we could draw a little graph here. So 6 over 5, let's just say that's right here, 6 over 5. We need to figure out what happens to the left of the graph and what happens to the right of the graph. So the derivative function, where is it? So just for simplistic purposes, we could say a derivative function is f over 3x, and then it would be equals to, but we can move 2 to the left side, so it'd be minus 2 equals 0. So let's plug in a number from the left side. So let's plug in 0 just because it's easy. So it would be 5 over 3 times 0, which is 0, so this would go away, minus 2. So our slope would be negative 2 at 0, which is a decreasing number, which means to the left side, we're actually going down. So we're decreasing on the interval from negative infinity to 6 over 5. And then to the right, we need to figure out what happens. So we could write it again. We have 5 over 3x minus 2 equals 0. So let's plug in, we could plug in 2. 2 would be right here. So we plug in 2, we're going to have 10 over 3 minus 2 equals 0. And we could rewrite negative 2 as negative 6 over 3. We have 10 over 3. So our final answer would be 4 over 3. And 4 over 3 is actually greater than 0. It's a positive number, so it's increasing on the interval from 6 over 5 to infinity. So we could deduct that our minimum value is right here at 6, comma 5. And also we should plug in 6, comma 5 into our original equation to get our coordinate. That would be the minimum, because from the left side it's decreasing and to our right side it's increasing. So we have deducted the intervals in which is increasing and decreasing. We have to find the local minimum. This is not going to have a maximum. We have to find the local minimum of this graph. So let's try to find that out now. Let's right here. So what's the original equation? We're going to have x to 2/3 x minus 3. Now we have to plug in 6 over 5 into this equation, which arguably is not going to be fun. So if we put 6 over 5 for x inside here, we're going to have 3. We could replace that with 15 over 5. So we're going to be left with 9 over 15 over here. And then on the outside, we're going to have 6 over 5 to the 2/3 power. And 6 over 5 to the 2/3 power is going to be roughly 1.13. And that's going to be multiplied by negative 9 over 15, which if we do that, it's going to be equal to negative 0.678. Or we could just write it as, negative 0.68. So our coordinate point in which the minimum value occurs is going to be 6 over 5, comma, 0.68. But 6 over 5 is also 1.2, so we could just write 1.2. But yeah, that's gonna be our minimum value for that, and our increasing interval is 6 over 5 to infinity. Decreasing interval is negative infinity to 6 over 5. Alright, so I want you guys to try number 5 and number 6. So essentially for these, this is the derivative graph, so you have to find out what interval it's increasing and then local maximum and minimums. So you can pause the video and try those out. Alright, so let's take a look at number 5. Number 5, first of all, they're asking us what intervals is f increasing and decreasing, and then local max and minimums, or x values of them. So first, let's kind of reiterate first derivative graphs. So when the velocity, or rather, when the derivative is positive, that means it's increasing. So for example, positive is increasing, and then when it's under the graph, it's decreasing. And in order to find out when there's a local maximum or minimum, you have to look at the zeros of the derivative graph. So that's going to be when it crosses the x-axis. So let's write down for number A, for letter A actually, on what intervals is f increasing. So increasing is when the line is going to be above the x-axis. So we're going to have first interval of 0 to 1, and then we're going to have 3 to 5, and that's it. And decreasing, let me write increase, and then decreasing is going to be from 1 to 3, and the interval from 5 to 6. And this is a 5 up here. And that's going to be decrease. And now B is asking us local maximum or minimums. So just so you can visualize it, if a graph is decreasing and then it's increasing, we have a minimum. And if a graph is increasing to decreasing, we have a maximum. So first we could deduct, these are the critical points of the graph. So at x equals 1, do we have a max or minimum? Let's figure that out. So local max. So it goes from increasing to decreasing. So increasing is going to be like that, decreasing is going to be like that. So that is a local max, x equals 1. And we also see that at x equals 5, it goes from increasing to decreasing, which is going to be another local maximum. And now that only leaves our local minimum to be x equals 3. But we could also see that it goes from decreasing to increasing, which is going to be something like this right here. So that's going to be our local minimum of x equals 3. Now let's take a look at number 6. Number 6 is going to be this little graph going on right here. So on what intervals is it increasing? So we just write increase. So it's increasing on the interval of, I don't think it's flatlining there, but yeah, so we just write increasing on the interval of 0 to 3. At least it doesn't look like it's flatlining there. But and it's also increasing on the interval of about 4.5 to 6. 4.5 to 6. And decreasing is occurring during the interval of only 3 to 4.5. So only decreasing on one interval. And let's go to B. So B, we have to find the local max and minimums. So let's take a look at when or where exactly it hits the x-axis. So it crosses it right here, and right here, and right here. So let's take a look at x equals 1. So at x equals 1, it goes from decreasing to increasing. So it's going to be something like that, decreasing to increasing, so it's a local min. Let's write out local minimum right here. So it's going to be 1 for our first value. And then at 4, it goes from increasing to decreasing. So it's going to be like that. It's going to be local max. So 4 is going to be our local max. And then 5 is going to be from decreasing to increasing. So it's going to be a decrease to increase, so local minimum. And those are our local max and minimums. And drawing these graphs out right here where it kind of shows the increasing and decreasing is pretty good way to, just check with yourself so that even if it's like second nature, you don't make a mistake. Alright, so I want you guys to try number 7. So number 7 is essentially, think of this as a function graph, first derivative and second derivative. So you have to find out the inflection point given the condition. So you can pause the video and try that out. Alright, so let's take a look at number 7 here, or rather A. The curve is a graph of f. So we pretend this is the graph of fx. As we talked about, the inflection point is essentially when the concavity changes. So we can see it's concave down up until x equals 3, then it's concave up and then down. So concavity changes twice here. It changes at x equals 3 and 5. So those are going to be our x coordinate for the inflection points. And now for f prime, so in order to find out when the concavity changes or the inflection point of f prime, we have to look at the minimum and maximum values of the function. So this would be like a f prime graph here. So the minimum and maximum values, basically what that tells us when it reaches a minimum and maximum is that the f double prime has reached 0 and it's changing sign. From like negative or it's positive to negative. So in this case, our inflection points would be x equals 2, 4, and 6. And now we go on to graph of f prime. So we look at this graph as a f double prime graph. Our inflection points would be essentially when the f double prime is going from positive to negative or changing sign. That's the most important thing. which happens at the zeros. So it crosses the x-axis twice, or actually one more time because it flatlines here. This would be like a x squared. So our inflection points here would be over here. So it'd be 1, x equals 1, x equals 4, and x equals 7. Or actually, it wouldn't be 4. I made a mistake there because an inflection point happens when the f double prime graph goes from one sign to the next. So here it's going from positive to negative, but here it's not going from positive to negative, it's going from positive to 0. And 0 isn't a negative number, so our x inflection points would actually just be a 1 and 7. Alright, so I want you guys to try number 17, number 18. So essentially for these questions, you have to find where it's concave upward and concave downward, and the inflection points. So if you remember, it's concave up and down means that it's accelerating or decelerating, which means that the acceleration is or the f double prime graph is either positive or negative. So you have to find that out. So you can pause the video and try that out. Alright, so let's take a look at number 17. Number 17, we have x cubed minus 3x squared minus 9x plus 4. So we have to find the second derivative in order to figure out the concavities and the inflection point. Inflection point is essentially when the second derivative is equal to 0, and then we'll figure out what happens to left and right. So let's find the first derivative of this. It's going to be 3x squared minus 6x minus 9. And then that is f prime of x. And f double prime of x is going to be 6x minus 6. And now all we do is just solve for x, so we could just add 6 on both sides. We're going to have 6x is equal to 6, and if you divide by 6, you're going to have x is equal to 1. X is equal to 1 is our inflection point. And if we kind of draw the graph of the f double prime, x equals 1 would be right here. And we have to figure out what happens to the left and the right. So in order to find out what happens to the left, we have to plug in a number to the left of x equals 1 into the second derivative function, which would just be 6x minus 6. So let's plug in 0 since it's to the left of x into 6x minus 6. We have 6 0 minus 6 equals 0. And we have 6 times 0 is 0 minus 6, which is just negative 6. So we're left with negative 6, which is a negative number, which means that it's concave down because it's the acceleration or the second derivative is negative. So we could conclude that in the interval of negative infinity to 1, it's concave downward or down. And we could just assume that after 1 it's concave up, but we could also plug it in. So let's plug in 2 into the second derivative. So it's going to be 6, 2 minus 6. And we're going to have 12 minus 6, which is just 6. That's a positive number, which means that from the interval of 1 to infinity, the function is going to be concave up. And what that is kind of looks like if I've visualized a graph for you guys, the graph is kind of going to look like, imagine like that. Like, okay, it doesn't like speed up that quick, but something like that. You see how it's concave up and then it's concave down here, all the way to x equals infinity. And it kind of flat lines here, which is the inflection point in which the acceleration changes magnitude or sign rather. So let's try number 18 now. So for number 18, let's delete this real quick. Oh, that was not what I want to do. But alright, so number 18 is going to be 2x to the third power minus 9x squared plus 12x minus 3. So if we find the first derivative, f prime is going to be 6x squared minus 18x plus 12. Now let's find f double prime, which is going to be 12x minus 18. Oh, 18. And that is our second derivative graph. Now all we need to do is just solve for 0 so we get the inflection point. And we can add 18 on both sides. So we're going to have 12x equals 18. Divide by 12. We're going to have x is equal to 3 over 2. So that is our inflection point, and now we need to find out the concavity in both directions. So let's draw another graph going on here. So this is 3 over 2. Let's find out what the concavity is to the left. So let's plug in 0 into the second derivative function, which is going to be this right here. So you plug in 0, we're going to have 12 times 0 minus 18. And 12 times 0 is 0 minus 18, so it's negative 18. So that means that the concavity is down to the left. So we can conclude that in the interval negative infinity to 3 over 2, it is concave down. And now let's find out where it's concave up, even though we kind of know that. So let's plug in a number to the right of 3 over 2. So let's plug in 3. Let's plug in 3 for the second derivative graph. So if we plug in 3, we're going to have 12, 3 minus 18. And 12 times 3 is 36 minus 18, which is going to be 18. 18 is a positive number, which means concave up. So we can conclude that from the interval of 3/2 to infinity, the function is going to be concaving up. And to visualize what that graph kind of looks like, it is going to be very similar to the other number 17, in which I can't be an exact in which how the graph looks. But obviously, it's going to be something like that because the exponents are to the same power. It's just the coefficients are different, which makes their graph look different, and is really not possible to tell exactly how it looks, but you kind of see how it's concave down to the left, and then to the right it's concave up. And yeah, that's basically it for number 17 and 18. Alright, so that was it for derivatives versus graphs. So essentially a takeaway from this topic is figuring out concavity, and as well as figuring out when a function is increasing and decreasing inflection points as well. And you need to figure out how to tell these figures in a graph on a physical graph and an equation as well. So the equation as well, you can find derivative, set it equal to 0, use the fundamental rules to figure out the concavity, inflection, and increasing points. And on a graph, you could visually kind of see where the inflection is taking place, where it's concaving as well as increasing and stuff. So the f function graph, f prime graph, and f double prime graph are the only ones you need to get really familiar with. So that's basically it.